This conference will now be recorded.
Great. Well, thank you, and thanks for the invitation to give this presentation. It's a real pleasure to talk about some of the work we've been doing, trying to look at this new, relatively new technology in the world. I pop up that I'm going to ignore. I've been using this technology since the late 1990s, and really in my day job, I look at earthquakes and volcanoes. And a few years ago with my colleague Andy Hooper, we realized with the latest generations of satellite, there was a technology here that had applications beyond the kind of our academic interest in those areas. So we've put a lot of effort into developing the technology, and in 2018 we spun out a company called SatSense in Leeds, which is still a relatively small company but growing very rapidly in this space. And you can read a bit more about us as a company and some of the technology in this article that was published in the PWI journal just last month, I think. So what I want to talk about here is, what's the challenge here? What's the problem we think this technology can address? And so then I'll explain how the technology works. I will really want to focus on some of the results from some work we've been doing, some R&D work we've been doing with Network Rail, looking at, in particular, what controls the quality of the data you get back from InSAR, because it's not a technology that works for all applications in all locations. So part of what I want to get across in this talk is what kinds of things can it do, what can't it do, what is it a solution for and what isn't it a solution for. And then I've got some examples of how I think some of the ways I think it can be used, with some of the validation work we've done so far. Okay, so obviously this is very familiar to all of you, but obviously ground movement or infrastructure failure, it has a big impact potentially on the rail network, and that can be from trains having to go slow, causing a delay, lines being closed, or obviously in very extreme cases, derailments. And so we'd like to be able to say something more predictive about ground movement and be able to manage that in a better way. So in this report by Lord Robert Mayer from earlier this year, some of the stats, again, you'll be very familiar with this as an organisation. It's 190,000 earthwork assets, and the vast majority of those are over 100 years old, many over 150 years old, and they continue to fail due to a number of reasons, whether that's construction, weathering, the soil types, drainage, vegetation management, and these problems perhaps are getting worse because of climate change. So longer periods of prolonged rainfall, more intense rainfall, and hotter, drier summers can all give issues. So the Mayer review also stated that InSAR is a promising technology which is rapidly developing and should be given further attention. And so part of what we've been doing with SatSense and Network Rail is doing that. So we're in collaboration through some R&D funding to really test the capabilities of InSAR now. So there was some work done a few years back by Network Rail on InSAR, but the technology is rapidly evolving and things have moved on. So I'm going to show some preliminary results from this project, and thanks in particular to Simon Abbott, Stephen Brooks, Manos, and Amy as well at Network Rail. So a bit about the technology. This is a sort of fundamental cartoon of how it works. Note it's not to scale, okay? So this satellites are flying at around 600 kilometers. Those wavelengths are about 6 centimeters in reality, so very much not to scale, this cartoon. But the general idea is that we're making precise ground movement measurements by comparing radar images acquired on successive passes of the satellite. And what we're looking at is the position of the wave in that cycle. So whether the wave comes back at a peak or a trough here, and we're comparing that between the two images, and we can compare that very, very precisely and get very precise ground movements out of that. We can do that with a single pair of images, or we can actually look at a stack of images acquired in the same place, and we can track those signals through time for an individual pixel in the image, and we can start to build up images like this. So this is the town of Ripon in North Yorkshire, it's a town that's prone to sinkholes. So what you might see if you're kind of eagle-eyed in the center there is a little red dot. If we zoom in on that, each of these colored circles is a place we've been able to make an InSAR measurement. I'll talk a bit later about where we can make measurements and where we can't. And then the color is the average velocity. And if you look here, the scale is in millimeters per year. So we're going from red, plus or minus, red is movement away from the satellite, blue is movement towards the satellite. And we're talking about rates of a few millimeters per year here. So it's still slightly mind-blowing to me that we've got satellites at 600 kilometers in the air and we're measuring things that are moving at millimeters. But I'll show you, hopefully convince you by the end of the talk that this technology really does work and compares very nicely with observations made on the ground. If we zoom in a little bit more, we can look at those pixels there, and we can get detailed time series of how those points, each of those points moves through time. So this is data from the Sentinel I satellite, which is a satellite I'll be talking about mostly, and that's been acquiring data since 2015. And since 2018, we've had data every 6 days. So there's an acquisition every 6 days, and you can see we're building up a time series there. And in this particular location, in August 2018, a sinkhole opened up in the center of Ripon underneath the Sainsbury's, and at that point in the marked by the arrow in the time series. So there's two things to draw your attention to here. Is actually before that sinkhole moved, there was a gradual steady subsidence. So there was this long-lived precursory movement that was going on for at least a few years before it moved. Then afterwards, we've also had some rapid movement that's perhaps due to whatever they've done, remedial work's been going on to sort that problem out. So we're seeing this be able to track that movement through time. So I thought it was useful to introduce some kind of key things that is useful for you to know about InSAR as a technology. First of all, it's not an off-the-shelf product. You can't easily go to the satellite provider and just say, give me some InSAR. There's a lot of processing involved, and there's a lot of bespoke algorithms that go into taking the raw satellite radar data and turning them into a movement product. So, and those algorithms will be slightly different from company to company. So it's a significant processing effort to do that work. I mentioned already that it doesn't work everywhere. This is an example, and I'll come back to this area. This is the Folkestone Warren landslide on the south coast. You can see the railway line running through the image there. And what you can see here, what I wanted to show you in this slide was that we've got good coverage where there's buildings. So this is a settlement. So there's houses there. We've got good coverage on some of the kind of bare rock areas, these kind of areas, but we've got poor coverage in the densely vegetated areas, and that's something that is a common pattern. So we get good coverage where the ground, the scattering properties within a pixel, when they stay relatively constant, we get a good scattering result. If you've got things moving, so in an agricultural fields, for example, if a farmer plows the fields, then that changes all the scatterers, and we're not able to track the movement there. If you've got very dense forested vegetation, the radar comes into the forest canopy, it bounces around in a rather random way, and that volume scattering again means we lose the signal. So it works in some places, it doesn't work in other places, and that's one of the challenges, one of the big challenges with InSAR, and I'll talk about some of the technologies we can use to overcome that. But it is a fundamental problem that means it's somewhat limited in some applications. What you'll notice, if I just delete some of my scribbles here, if you look along the railway track here, railways are interesting because you've got features that are stable and don't move very much, and then often there's vegetation along the cuttings as well, so cuttings and embankments and along the tracks. So you have actually got some scatterers coming back there, and often you're getting some measurements along bits of railway as long as they're not very densely vegetated. And I'll quantify that later in the talk. how often it works and how often it doesn't work. So another thing to know about InSAR is it measures essentially movement in the direction between the satellite and the ground, and the satellite's looking sideways. So there are essentially two viewing geometries. One's called an ascending pass, and that's when the satellite's flying from south to north and looking to the east. And I think to explain this is if you imagine looking straight, like we like a satellite down, by measuring the distance to the ground, you've got sensitivity to the distance in that direction, but you can't see any movement horizontally. Now it's sideways. So we have no sensitivity in this plane that's perpendicular to the look direction of the satellite, but we can measure any movement, any component of movement that gives us, any movement that gives us a component of change in distance to between the ground and the satellite. So if you look at the diagram here, if the real motion is in the direction of the green arrow, what you measure is the movement there by the blue arrow. So you don't see the full component from that geometry. And I can demonstrate this with some beautiful landslides that we pick up. These are in the northwest. This is the valley here, and those landslides are moving down the hill there. They're moving towards the satellite in that case. So, and I think they're moving horizontally largely, but also slightly down, and you end up they're colored blue because they're mostly moving towards the satellite. If we look in the other direction, which is the satellite flying, the descending pass, which is the satellite flying from north to south and looking west, so looking in the direction of the arrow there, what they're doing now is those landslides are moving towards the satellite. They're now moving. Sorry, they're moving away from the satellite, and so they're coloured red. So what we're seeing is a combination of the vertical and the horizontal movement. Most of the time in the UK, the vertical actually dominates, but sometimes in examples like this, the horizontal matters. So if I just flick between the two, you can see the landslide areas move from blue to red in those two viewing geometries. And you can combine those two signals to create east-west and vertical movement, and you can separate out those two. We have a little bit of sensitivity to north-south motion, but very, very little. So actually, if your movement is strongly north-south, it's challenging to see. So essentially, we see two components of the 3D movement. The other important thing is that the satellite isn't acquiring data continuously. It's not a geostationary satellite pinging data every few minutes. It's there's an acquisition every 6 days for the Sentinel I satellite on a single viewing geometry, and that's from two separate satellites. So so you actually can't. This is not a technology that's going to give us an early warning if a sudden landslide has collapsed, encroached on the track. You're going to know about that before the satellite knows about that. So it's not an early warning technology in that respect, but it's potentially a long-lived warning system. So it's something that can give us hints of the kind of for signals for collapses that have a long precursory motion. That's where it has its power. There are a bunch of satellites that fly up there. And I think the ones that are important are at the moment the Sentinel I satellites, and that's a lot of what we do in SatSense is with Sentinel I data. It's globally available, it's free, it's a moderate resolution, so around 10 meters resolution. NISAR is another mission, a US-India mission that will be launched in a couple of years, and that will also be global and free, and that will also be important. If you want higher resolution, so down to kind of 1 to 3 meters, there are missions like TerraSAR-X, Cosmos SkyMed, and some really interesting future missions that are coming online from systems like ISAR that potentially can provide daily, very high resolution imagery, but only for very small areas, and you have to pay for them. So there's a balance there depending on the application, and I'll compare some results from the two from Cosmos SkyMed with results from Sentinel I, so you get a sense of the scale of what you can see with each system. I think Sentinel I is a real game changer, and it's the reason we set up SatSense. So it's operational. So it's the first really operational radar satellite. Before this, they've all been kind of research missions really, rather than operational systems, at least the non-military ones, I should say. So all radars are all weather. So one of the advantages of radar satellites is you see through clouds. They work day and night because you're actively illuminating the ground from the satellite. So Sentinel I has systematic acquisitions over the whole planet. So there's at least one image every 6 or 12 days, depending on where you are in the world. And in the UK, we actually get 4 images in 4 different viewing geometries every 6 days, because we're quite a long way north, so the neighbouring tracks overlap. So we get information from overlapping tracks. So we have 4 separate time series that we keep up to date, and every 6 days we get one new data point in each of those 4 time series. The other nice thing about Sentinel I is it's designed to do this kind of technology, and what that means in practice is it's got a really boring acquisition schedule. It just gets the same data every time it goes over. It's exactly the same, and that's what you want for this technology to work. There's a lot of the other satellites have all sorts of fancy modes. You can do spotlight, really high resolution, moderate resolution. You can point in different directions, but what that means, you can only do this InSAR work if you've got the same mode acquired again and again. And so Sentinel I's great for that, because it's just the same all the time. And it's funded for 20 years, and actually they're already planning follow-on missions. So Sentinel 1A was launched in 2014 and 1B in 2016. And the data are free and open. So the motivation for SatSense was to change our business model. So instead of people coming to us saying they want some data processed, we go away, process the data, charge the customer a lot of money. The idea was we would just process the data all the time, assuming the customers would eventually come, and we can sell you, if you want just data for your one house, we'll sell you that, your one bridge, we can sell you that, or if you want an entire rail network, we can sell you that, and it's available instantly. So it's a different way of working. So we have an interactive portal you can go and look at and see the data for the whole UK, and just go and click on different points. And if we have time later, people who hang around can have a play with that. I said I'd compare the resolution from the higher resolution systems from Sentinel I. So on the left here, there's data from the Cosmos SkyMed satellite system. This is in Battersea in London, and this Cosmos SkyMed, in the data we've chosen from it, has a 3-meter spatial resolution. And on the right, there's the Sentinel I data, which we process to give pixels every 4 by 14 meters. So you can see the difference there, that actually when you get down to individual pieces of infrastructure, the Cosmos SkyMed data really localizes much more precisely onto the infrastructure. With Sentinel, you're really getting a kind of an average view in most cases over a pixel. You can think of a cell on the ground 4 by 14 meters or so. So it's really what's coming back from that, more of an average view of the movement. So depending on your application, you may find the Sentinel I not high enough resolution, and you'd need to go to something like the Cosmos SkyMed system. Unfortunately, for things like Cosmos SkyMed, you're paying hundreds of euros for every single acquisition. So there is a big price jump to go from one to the other, and that's not us at SatSense. That's the data providers. So really, what we're trying to do in SatSense, and this is the most salesy slide. I'm trying to, most of the rest of the talk will be trying to be a bit more objective about where the technology works and where it doesn't work. But I think what makes us different is we're doing large-scale processing. We're keeping huge areas up to date, and you can go and get those data instantly. We're also doing a lot of work that's turning those red and blue dots into information. So actually, I don't really want a red and blue dot. I want to know, is that amount of movement a problem? Is that going to cause damage to my building or to my track? And we're doing a lot of work that's about getting our data into other people's systems, so via APIs and web mapping services and things like that. And we also have this interactive portal. So those are the main things. Our algorithms, we think, give higher measurement density than many others, but that's into the technical detail of what we've been doing. So, okay, I think one of the key things we wanted to look at with the project with Network Rail was understanding and quantifying the controls on InSAR quality. So when does it work? When doesn't it work? That's what they wanted. Network Rail really wanted to know. So how often can we apply this as a technology? So for the first part of this project, what we've been doing is testing the performance of our Sentinel I data in sites in Kent, many of which are instruments. So the sites we've been looking at in Kent, and what we've been doing both the InSAR coverage, and so the coverage is about whether we can make a measurement or not. So we define that explicitly as the percentage of an area that has InSAR data within it. So if you think about each InSAR pixel covering a patch of ground that's marked by one of these green boxes, we look at all the data from all the tracks, and we say within a 25-meter buffer of our site of interest, what percentage of that buffer is covered. And so in this particular case here, we've got 46% of that buffer is covered. And so we've got successful data there. And this is the kind of histogram we get out. So on the bottom here, hopefully those of you in the room can see we're going from 0 to 50% here, up to 100% here. What you can see is that around half of the sites are pretty poor, so less than 20% coverage. And around a third of the sites have more than 40%. So that's roughly, and of course, a caveat here is that if you've got 80%, but your site of interest is in the 20%, then the data is not very useful. And if you've got only 20%, but your points are on your object of interest, then it is useful. So this just gives you a feel for how much coverage we've got with Sentinel I InSAR. And then we also quantify the noise, really just looking at the scatter in the time series. So here's 2 data points. This is actually in Wakefield. So this is the East Coast Main Line here going into Wakefield. And Wakefield suffers from some coal mining, ongoing coal mining subsidence. And you can see that there are 2 different points there. One of them is relatively clean and one of them is quite noisy. And so we quantify that as well. And again, you get a histogram of the RMSE. And what we do is then try to put those together into a kind of a high quality, medium quality, and low quality by combining the coverage and the noise to give an overall estimate of the quality. And we're doing that automatically from metrics, and we've also looked at it ourselves and said what's our feeling for the quality of this site, and those numbers were fairly consistent when we did it with the metrics and when we did it by hand. So I think the metrics are a reasonable way of doing that. You can get a quick view of a site fairly easily just looking at the metrics. So I think InSAR is what we call potentially useful. So with at least medium quality data in 60 to 70% of the sites. And this is using, another caveat here, this is using 76 sites in Kent. So it may well be that those numbers are different on different parts of the network in the UK. And they'd certainly be different if we were looking at a railway through the desert in Australia, where we'd get fantastic results. So it really does depend on your conditions. So once we had that data, we then looked at the controls on the quality. So what really matters? What are the things that control the quality? So first of all, asset type. That didn't make a huge amount of difference. What we were looking at, the orientation makes a little bit of a difference. So east-west and northwest southeast seem to do slightly better. So we were slightly surprised by that. There's quite a range for all of those bins. Obviously, the satellite is looking east-west in one direction. So my prediction was that the north-south would have been better than the east-west because we've got more things perpendicular to the track. But it's actually the opposite was what we found, which is always nice to be surprised. The big control here is vegetation density, right? So if we've got dense vegetation, then we've got low quality InSAR. If we've got sparse vegetation, we get good quality InSAR. And again, if you look at the vegetation type, trees and shrubs tend to be worse than grass. So, and that's really to do with how quickly they grow, how much volume scattering there is in the vegetation canopy. So how much of the ground you see. So bare rock and grass we normally do quite well. Shrubs, you can see again really wide range for both of those. So there are places with trees where we do get good results, and there are places with grass with shrubs where we get good results. So it's always worth a look. The geology doesn't make much difference here. I won't dwell on that. And again, what's being reflected off doesn't make a huge amount of difference. So unless it's vegetation, if we think the dominant reflective surface in a pixel is vegetation, we don't do very well. And then broadly speaking, where the railway goes through a town, we get better answers than where it goes through rural areas. If we did this analysis for random points in a town, it would be versus random points in the countryside, the difference would be even more dramatic. But because a railway, as we talked about before, if you're in a town, the railway track is often more vegetated than the rest of the town. And if you're in the countryside, it may well be less vegetated than the rest of the countryside. So that kind of equalizes things a little bit. But in general, we get slightly better results from urban railways. So just to put that together, really, the dominant control on InSAR quality is the vegetation level. Dense trees and shrubs give poor coverage, but there is a wide range of InSAR quality for most cover types. So often it's worth a look at the data, because we are often surprised. So there's rules of thumb here, but there's not a, you might get good results anywhere, and you might get bad results anywhere. One thing we can do to improve the results, if the results from the natural scatterers are bad, is use artificial reflectors. So these are corner cubes that you can put out in the ground. There's some photographs of a few different designs there, and the idea is it's a bit like hitting a snooker ball into the corner of the snooker table. The ball comes straight back at you, and the same is with a radar. With the three surfaces, whatever angle your signal comes in at, the radar will bounce straight back in the direction it's come from, and so you get a very, very bright return. These are different designs for corner reflectors. This is on the left here is a very small corner reflector designed for high resolution data. That's on Waterloo Bridge in London. So next time you're in London, just have a look on the side of Waterloo Bridge and you'll see those reflectors there. Here's some examples of what the difference they make. So on the left, this is in a site called Hurstmonceau, which is a geodetic testing site in Surrey, I think, or Sussex. On the left is the radar image without the reflector. On the right is the radar image with the reflector. You can see the reflector coming up very brightly there. If you look at the phase, which is the component of the signal we're really trying to measure, if you look at a point in the field and you compare it to a stable point somewhere else, you can see there's a lot of scatter there. That's basically a useless point. If we look at the location of the reflector, before the reflector went in, the point is useless. There's just lots of scatter due to the vegetation. After the installation of the reflector, that phase is very, very stable. So we're actually getting a really nice stable reflector there. So what you can do, what the corner reflectors are doing, are increasing the amplitude, so increasing the strength of the signal back to the satellite and reducing the scatter in the phase. So the size of the reflector that you need depends a little bit on the conditions, depends on the satellite and the required precision. Typically, these are on the order of 1 meter for Sentinel I and 0.5 meter or less for higher resolution systems. And one of the things we've been doing in SatSense is designing some smaller multi-reflectors, so looking at the idea, instead of putting one big reflector, can we just put a few smaller ones in there, so we have a nice design that does that, which can also reduce the footprint on the ground. And we're currently working with Network Rail to test some reflectors trackside over the coming year. So we're just at the point of deciding which bit of track to put them by, that I think we'll learn a lot actually in that process, just about how we attach them, how, the practicalities of using reflectors. So how do I think we can use InSAR for asset management of the railway infrastructure? I think there are 4 general ways. I think the first is to kind of aid with the monitoring of sites that we know about, so known sites of concern that are already being surveyed with instruments on the ground. So to complement the ground-based observations, increase the quality of those. The second is to look at the whole networks and actually screen whole networks for anomalous movements. The third area is monitor processes occurring, so somebody building something that you as a railway operator that's going to impact on the railway. Fourth one, which is the hardest, is kind of doing alerting. And I've kind of already said we're not going to be giving you real-time warnings that there's been a landslide, but perhaps we can do kind of short to medium term warnings where we're talking about weeks that something anomalous has happened. So I'm going to go back to Folkestone Warren, which has been I think a problem for Network Rail ever since the railway was built there. This is a spectacular landslide in 1915. And I showed you some of this data before, but just to, if you think of most of the signal here as being, it's a combination again of vertical and horizontal, but in this case, the vertical is dominating in this geometry. So you've got the head of the landslide up here and that's subsiding, and you've got uplift down here in blue at the toe of the landslide. And again, you can look at time histories here, and you can see there's both steady movement and periods when it's accelerated. Now, this is a site that has very dense observations on the ground from the geotechnical team, the local geotechnical team, and we've been trying to compare those observations and do a kind of quantitative assessment. How well does the satellite observations work? And it's a bit of a busy diagram, and I think the details don't matter too much, but the big squares in this case are kind of averages of the InSAR data within those big squares, and all the triangles, for example, around there, those are individual peg monitoring sites. So these are pegs on the ground that are monitored with total stations, typically once every month or every few months. So their positions are tracked through time. And what we've done here is taken the 3D movement measured at the peg and looked at how much movement we would expect to see in the satellite geometry. And already just visualizing that, you can see you've got red points where you might expect red points, white where they're white, pink where they're pink. So there's a reasonable qualitative agreement there, just looking at the data. And if we look at the different viewing geometry, this is looking as the satellite flies. This is the descending pass as the satellite looks from north to south. And again, it changes the colors a little bit. You can see some of the red areas now go blue, and that's largely to do with the combination of horizontal movement, which we can't see in this direction. But we can see the horizontal movement in this direction. There's some movement towards the satellite there in the horizontal. What we can look at then is the velocities and do this in a quantitative way. So if we take each of those pegs and each of the InSAR velocities in all of our different viewing geometries, and we can just plot one against the other. So on the bottom here, we've got the velocity of the peg, and this is from the satellite here. And you can see there's a fairly good correlation. It's not perfect. If you look at a histogram of the difference, then they agree to around 7 millimeters per year. And when we look at the scatter in the individual time series, you can see that some of that error is coming from the InSAR, undoubtedly, but some of it's coming from scatter in the peg measurements as well. So you can see here's this top left one, you can see the peg data in blue is relatively noisy itself. So those ground observations aren't perfect, but you can see here comparing the slope of some of these lines that you've got here. I've picked a few different sites, somewhere like this one where so the InSAR is only covering a relatively short period, but if you compare the velocity of those peg points in the same time period, you've got good agreement even down to this little dip here towards the end. This one here, it's been monitored less frequently by the peg data. The peg data seems to have a jump there that we don't see in the InSAR. I'm not sure whether that's because there's an issue with the peg or whether it's an issue with the InSAR. It's something we would have to look into and dig into a little bit more detail. This is one of my favorite comparisons. So this is a bunch of pegs that are on one of the retaining walls, and you can see that in all of the pegs they have this kind of nice decaying pattern that started in 2021, and that's seen very mirrored really perfectly in the InSAR data as well. So we're getting a really nice agreement there. So one comparison we've done is, instead of looking at the individual velocities and comparing those because they're a little bit noisy, what you can do is compare the positions at any one time for all of the time series for all of the positions, and then you get a graph like this, which shows the displacements of the pegs on the ground versus the displacements from the InSAR, and really actually we're almost embarrassingly good correlation there when you do it this way. We were quite surprised. So this is, and the standard deviation here is about 10 millimeters. So that's saying if you take any one instant and look at the position you're getting from the InSAR relative to the start of the time series, then the peg and the InSAR will agree to about a centimeter on any one instant. So the average velocity will agree better than that because you're fitting multiple points with individual errors. But for any individual point in any one time, we get about a centimeter of agreement. So we were pleasantly surprised when we plotted that up. So hopefully that convinces you that what we measure with the satellites is correlated with what we see on the ground. What we'd like to be able to do, so I think the application here then is really, we've got observations in places that there aren't peg data. We can look more frequently. Actually, the pegs are often being monitored once per month or so, and we're getting data every 6 days. So can we, I don't think this technology is a technology to replace boots on the ground, but can we design monitoring strategies that combine what you get from instruments on the ground with the satellite data to come up with a better product, better monitoring solution, potentially at lower cost? Because obviously every time you put boots on the ground, it's an expensive thing to do. So the next potential application is screening networks for anomalous movement. And again, the idea here is that we'd like to identify places with long-term movements before the failure occurs. So I want to show you movement at East Grinstead landslide. And this is some data. This is an example that's in the article we have in the PWI journal. What you can see is again, very similar to that, to the sinkhole that I showed earlier. There's a long precursory movement here that reaches about getting on for 2 centimeters of movement in the around 3 to 4 years before the failure. And of course we don't know how long that was going on before the failure. After the failure, we've got some movement that's largely probably associated with any remedial work that's going on. So I think actually Network Rail are quite good at identifying and remediating slow-moving failures. The data you get from the survey trains, for example, give you some quite nice information on that. But I think the question there is, can InSAR make further improvements or help prioritize remediation work? So the analogy, we do some work with water utility companies, and again, it's a similar problem. They're replacing 1% of their network the water pipes, 1% of it's replaced every year. They want to prioritize the 1%, so they minimize the number of leaks. And so can we help prioritize the remediation work by looking at places of known movement, but also places of unknown movement? So one of the more challenging things we were asked to do as part of this R&D work is to do a blind test. So how well can InSAR distinguish between stable and unstable sites in a blind test? So we took those sites in Kent and we classified them based on the InSAR data before we were told what the ground movement was doing. So this is from our side a genuinely blind test. And then we did the same. Then we got the information from the pegs and could classify the movement from the pegs. And then the idea is to build one of these truth tables. And I think since COVID, we've all gotten much more familiar with understanding false positives and true positives and Bayes' theorem for understanding whether this is useful statistics and all of this kind of stuff. So or maybe I've read too many of those articles about it. But the idea is if you've got movement that you see in the pegs and the InSAR, we've said this is a site that's moving, that's a true positive, etc. Okay. So I'll just show you a couple of the peg time series. So the very simple classification, this is following the approach that Network Rail are using to monitor those. You just plot all of the pegs, the magnitude of the movement. If it goes above 30 millimeters a year, it's amber. If any of the pegs go above 30 millimeters a year, it's amber. If it's 60, it's red. If it's 90, it's black. So there's an amber site. Here's a very large movement of those sites with some variance at some of them. And so the 76 sites that we looked at in the first part of the study, 50 of those have peg data, of which for InSAR coverage, and actually 40 have any InSAR coverage and 36 have moderate or high quality InSAR. And there's a mixture of green, amber, red and black amongst those sites. And just to give you a sense of the InSAR data, this is again the work we did prior to the peg analysis. Here's a site where there's no information around that site. This is an example with very, very dense trees near the track. Really, the InSAR's done a very poor job there. And there's a couple of other sites where the InSAR data has done a reasonable job. We've classified this one here as a kind of possible movement trend because it's not really a long-term trend. It looks like there was a pulse of movement in that particular site, whereas this site at Oak Lane here was more of a steady movement through time. So that was a clear movement trend there in that particular classification. So we had, this is the kind of spread of, for the full 76 sites, the spread of, we had a mixture of stable, possible and clear trends amongst those sites. And this is the bottom line, okay? So for where we said the InSAR showed stable movement, I think we had most of those also were stable, and where InSAR said there was movement, most of the sites were moving. And if we look at that in a truth table, I think the first thing to say is that there's a real qualitative difference between those two histograms, the ones where we said there was movement and ones where we said there wasn't movement. We haven't got it perfect, but we were really encouraged by that. And then when you look at it in a truth table, so we've got we've got more things in the true boxes than we have in the false boxes. We end up with about 78% of sites classified correctly from this blind InSAR analysis, where we've got the InSAR coverage, I should say. And this is, I mean, actually, again, this was something that is almost too good, partly because a lot of these PEG sites, there's only 2 years of data where we're comparing it to 5 years of InSAR data. They're not necessarily in exactly the same location. Often we've got, so there are lots of reasons why lots of excuses we have ready up our sleeves for why this wasn't going to work. But it seems to have, it's encouraging. And I think the jury is still out as to whether this is useful in the long run. I think this is a very targeted subset of 76 sites, and those 76 sites have been chosen because a lot of them are sites of concern. So more of them are going to be, this is where Bayes' theorem comes into it, right? So if your COVID test has a 1% false positive rate, and only 1% of the population has COVID, and you test everyone, then half the time you're wrong, roughly. Whereas if 50% of the population has COVID, and then you're most of the time you're right. So I think if you apply this technology to most of the network, where most of the network isn't moving, we're going to get more false positives than this. So I think that's where I think we need to factor in those kind of things. And so there's a bit more thinking and a bit more research to work out how this data can be used. And my feeling is using it, what we've learned with the water utility companies is you don't use it necessarily in isolation, you use it in combination with existing knowledge. So your network rail already have an idea of which sites are moving. Can we help prioritize within that list? Can we bring some other sites into the list where it's very, very clear? Can we say, actually, yes, all these sites are moving, but these ones are moving. It seems to be a much bigger problem at these sites than these other ones. So using it in combination, I think, is probably going to be the solution. So I think an easier way to use it actually is monitoring sites beyond the boundary fence. So construction, mining, waste dumps, anything that happens beyond the bit of the network that is owned by Network Rail can pose a risk. And often these are only inspected visually. So here's an example. Again, this was one from the PWI article. This was a new distribution center that was built right next to the track in near Rugby, and you can see the settling signal, nice settling signal in the time series here. So through time. So that's something where you can clearly monitor that. You can look at that through time. We can provide products that show where there's new construction, for example. This site here is an overburden mound or something like that at Shotton Surface Mine, and again the railway track runs through there. And again, you're seeing the movement. You're able to monitor the movement of that overburden mound. And so that's a relatively local mining signal, but also much more broader mining signals. So this is in South Yorkshire, and again you've got, so it's interesting that the signals you get now from coal mining, you get some bits going down and you also get some bits moving up, and often it's actually to do with the way water's moving in the subsurface, and it can be modeled, but it depends very much on you know, how the parts are being used. The data can provide those kind of broader scale signals that might warp a track over a longer wavelength that'll be very hard to see actually from looking over the fence. So finally, the final potential application is alerting. This is a non-rail example from Sakthi Selvakumaran at Cambridge. She did as part of her PhD. She looked at some data at Tadcaster Bridge, which collapsed due to scour, and actually that collapsed pretty quickly. And she looked at this with TerraSAR X data, one of the high resolution data sets, and she found that this is the kind of normal range of movement, and then just before the failure, it did come outside that normal range. So that was potentially, this is one of those cases, if you'd have had that data and you've been looking at it at the right time, potentially the satellite data could have shown you something. If we go back to Folkestone, we've got information, the vertical lines on these time series are times of individual failures. And the interesting thing here, I think, is that some of the failures happen when there's accelerated ground movement and some of them don't. And I don't understand why that is, and we'd probably have to go and individually look at those failures and the locations of them. We had a look at this one in particular, the failure that is labeled 2535 there, the right-hand side of those two vertical lines. So failure here, and we just looked at the movement that happened from the previous failure to the next one, and what you could see then is all these red areas are the parts that moved in that very short time window between those two failures, and the failure is there within that area that had moved. So again, there's potentially something here. There's all sorts of caveats here. So I work on earthquakes, and earthquake prediction is one of those things that's mostly a real scam. There's a lot of charlatans out there doing this kind of stuff. So anytime we talk about predicting things failing, I get really just naturally nervous about it. And so providing robust, reliable, short-term alerts, I think, is challenging and needs more work. It's always much easier to look back at a known failure and say, oh, look, something funny happened before that failure, To actually do it the other way around and say, look, here's a bunch of funny things, and then before the failures happen, is much, much harder. And of course, that's what we'd like to do, to be able to predict things before they happen rather than afterwards, when it's not very useful. And I just want to repeat the point about the timeliness of this. We're not ever going to be doing short-term failure prediction. You know, even in this case, we're talking about movement that happened over perhaps a few months. But maybe we could get down to a few weeks to a few months. But the shorter the time, the less reliable this is going to be as a technology. So anything that's failing rapidly, this is not the solution. Okay, so I think I'm ready to wrap up. So I thought it'd be worth summarizing advantages and disadvantages of this technology for asset monitoring in rail. So millimeter accuracy, weekly updates, so potentially saving money through reducing the number of boots on the ground. High measurement density if the ground cover's suitable. 4 measurements every 6 days for Sentinel I. We can monitor potentially a large fraction of the network, not all of the network. We can look at sites beyond the boundary fence, and we can go back in time as well. So if you're starting to monitor, if you're monitoring a new site, you can only monitor forwards in time. Whereas with the satellite data, we can look with Sentinel I, we can go back to 2015, and there are other satellites that let us look further back in time. So you can get some kind of understanding of what might have happened at a site before you started to monitor it. So disadvantages, I think obviously the main one we talked a lot, corner reflectors can potentially overcome some of that. But of course, then we need boots on the ground to install corner reflectors. Some of the future satellites, the US satellite I mentioned has a longer wavelength, and that should do better at seeing through the vegetation. It will do better at seeing through the vegetation. So this, again, these technologies will evolve and improve. So yes, reflectors are likely required for some sites. We can't see the very rapid movements, and the spatial resolution, at least for Sentinel, might be too coarse, and so you need the higher resolution data for some sites, but of course that's more expensive. We can't see north-south motion very well, so only sensitive to vertical and east-west. And if you have a really rapid movement, you can lose the signal as well. So just to summarize then, some conclusions. So I think the results we're getting from the SatSense InSAR data are correlating really nicely with ground movement monitored by Network Rail. The blind testing shows that the data potentially can be useful for identifying sites that are unstable. InSAR quality is highly dependent on the ground cover, so it doesn't work for all locations. But I think, having said that, the technology has matured over the last 5 years or so, and I think it's now a proven, robust technology that I think does have an important role to play alongside more traditional technologies. It's not going to be the solution for everything. It's not going to replace everything, but I think it's a technology that should start to be used more routinely for asset monitoring in rail infrastructure. So I will leave it there, and thank you very much. Okay. So I don't know how you want to run the questions. I'm happy to take questions.
Okay, I think I'm in control of the microphone. So if we take questions in the room, I'll either repeat the question for the benefit of the people who are remote, or if they're a very technical question, I might actually hand the microphone over to the person asking the question. I'm going to take the privilege of, since I've got the microphone on me already, asking a question about the, you mentioned Tadcaster Bridge, yeah, and the fact that the results over time seem to vary quite widely. Is there a, do you think there's a prospect of the InSAR being able to characterize the seasonal shrink swell of earthworks with a view to perhaps detecting where underneath you might the shrink swell might actually hide an underlying potential failure in the future?
Yes, and we certainly see seasonal movements at some sites, and it's something our data isn't optimized for, but it's something we do see, and we can. One of the things we want to do actually is do some optimization to pull out this, to actually explicitly pull out those seasonal signals. But yes, we do see that, and I think one of the next things we're doing with Network Rail is actually, rather than looking at the correlation between our raw or InSAR data, is to actually look at things like, you know, a seasonality index, and perhaps looking at different filters, so looking at the gradient of movement or the different wavelengths of movement, and seeing how they correlate with failures. And certainly seasonality is a key thing we want to look at, and we definitely see that in the data. Yeah.
Brilliant. Thanks, Tim. Okay, if I open it to the floor.
Right. So I was just wondering, Tim, if you have, if you're looking outside the boundary fence, for example, and somebody did some major, deposited a lot of material, would that be detectable? Because, or the fact you changed several wavelengths worth, I mean, it was just, you couldn't make sense of it. So does it have to be a sort of small, predictable, regular movement for it to actually?
Yeah, so to get a deformation measurement, you would need it to be, it wouldn't work for that particular application, but what we would get is a break in our time series. And one of the products we're developing, hopefully over the next few months, is actually something that tracks exactly that. So when has something changed? So one of the byproducts of what we produce is a product called coherence, and coherence is a measure of the it's basically how much scatter is there in the phase. And if you've got something like that, what you'll get a spike in the amount of scatter, so you'll lose coherence for a short period of time. And so what we want to do is track those and identify those, and actually come up with a product that is just flags anything new that's been built, you know, without any kind of diagnostics of what they are, just says something's changed here, so go and have a look. Yeah, and that can be done. I should have brought the little movie. We've got a nice movie of one site being constructed. You know, if you've got things being built over a 6-day period, you can really see, you know, over months, you know, you can see them with the 6-day acquisitions. You can see buildings being built, and so it works quite nicely for that. But it does mean we wouldn't be able to track the millimetric scale movement across that construction. So you could measure it before, you can measure it afterwards, but when there's change going on, you lose the signal. Yeah. Okay, good question.
The question I've got is, do you think you'll ever get to a position where you could actually proactively go to a client or a local government and say, we've got a bit of information if you want to pay for it, which may save you millions of pounds?
Yeah, that would be nice, wouldn't it? So I think maybe. I mean, it's people don't like getting bad news today. This is part of the part of the issue here. Give us. Yeah. So indeed. So I think one of the things we're doing a lot of work on is you know, along with a lot of people, is machine learning kind of algorithms. So we're doing some work. You know, and my colleague Andy is doing a lot of work kind of academically, and we're doing exactly that kind of work for volcanoes, tracking all the volcanoes around the world, trying to use machine learning to flag anomalous behavior. And we've been doing some similar work in the UK with colleagues in Bristol, and there's some preliminary papers out from that work that you can flag, you can use those algorithms to flag movement. I think there's more work to be done, and I think that will be the way to do it. So hopefully, yeah, I think there's value in there, and it's just, again, knowing what people want to know and what people don't want to know. I mean, and how, and who's got them, what people are prepared to pay for. Yeah, and yeah.
Hi Tim. Thanks for the talk. I know that Network Rail are doing work with you, and they've also been doing some work with AECOM on the data that comes out of the track recording vehicles and new measurement trains and so on, and the embankment instability metric, I think, that's been developed. Has there been any sort of coming together of these two technologies to sort of verify each other, or
There hasn't yet, but I think that would be a great thing. It's kind of, again, an obvious thing to do, particularly if we start to do, rather than looking at just 76 sites, start to do kind of network-wide assessments, and being able to look at those kind of data together. It's kind of, I think they could potentially marry up quite nicely, I think. It would be.
And I suppose the other question I have is, I guess what we all want to get to is something that predicts the future. But from what you were describing, you collect the data's all there. So you have a record of the past that you could access at any time if you wanted to go back and look at something in more detail where something has happened. Is that the case?
That's right, yeah. So I can say, after we've done some Q&A, if people want to hang around, I can do some live demo on our interactive portal, and we can just go and have a look at different sites around the country and see what's going on. But yeah, so it's always easier. Yeah, predicting the future is hard, as I said. So, but one of the things, I was trained as a geologist. The past is the key to the present is one of the kind of classic things that geologists get taught. Or the present is the key to the past as well. It's the other way around. But yeah, I think you can, if you can look at the past and see what has happened, you've got some hope. I think it's one of the inputs there. That's not the only thing that's going to tell you about a failure. You're going to want to build models that incorporate weather and knowledge of geology, local knowledge of how things are behaving, and bring all that together. But I think the InSAR can really just as a massive data set that's there and available, and I think it's, in my mind, it's a no-brainer. It's not going to work all the time, but it's where it does work. And so it feels like it, and how to get having access to the data via a portal, or whether it's much more abstracted and we're just helping, somebody more centrally just helping prioritize remedial works. I don't know, but I think there's information there that's not available from other sources that I think is valuable.
Yeah, and I suppose from what you were saying, in theory, you could look at the whole of the network all of the time.
Yeah.
But clearly that's going to be quite expensive and time consuming potentially. That's what I'm postulating. It may not be true. It may be easy.
I think it's easy. Yeah.
Oh, okay. Well, if it's easy, then it's a kind of why not?
Yeah. I mean, I think we process the data for the whole country. So I think at the moment, within 24 hours of the satellite overpass, we've updated the time series, and we do that for the whole country. So I think extracting that automatically for an area of interest, we already do this for other locations, and so it's entirely
it's
feasible.
It's a matter of when you see something which somebody really needs to know about, isn't it? And being able to.
Yeah, and it's working out whether it's how much of it can be automated in terms of machine learning algorithms, or how much of it needs a trained analyst to go through and look at those signals. What we can do to make that easier for people, and understand. And I think, again, we know it's not going to work all the time everywhere. So understanding when it doesn't, when the data doesn't look right, and when it looks like it's good, and how we can try and make that easier for the end user. I think that's what we're trying to do at the moment. Yes, I'll look at a site and say, okay, I don't really trust that point, but I do trust that point. Yeah. But that's because I've been looking at this kind of data for too long. But I think it's making that easy for people. I think is part of what we want to do. Yeah, exactly. But yeah, I should put that up as well. Yeah.
If you're designing a site, have you got some guidance on what to include so that this can be used?
Yeah.
Or if it's impossible because you might want to put vegetation for aesthetic reasons or something, what's the kind of coverage that you would need on the corner reflectors to provide the suitable coverage?
Yeah, so I guess it depends on, I think it would be that would be a case of looking site by site. So, and it would depend on what you were worried about, right? So if you could imagine a site where actually your measurement every 100 meters along a long embankment would be sufficient, in which case you could have a little, thinking out loud, a little clearing every 100 meters with the reflector in it, and then you could track those, or you might want them more closely spaced than that. So I think it would depend. You could certainly design a site so there was a combination of vegetation and reflectors. You put them on, have retaining walls, or I think with the reflectors you can also increase the size. The bigger they are, the more they dominate the background signal as well. So for sites with not much background, quite small reflectors are okay, but when it gets if you've got lots of other things in the site, you start to need bigger reflectors, and the reflector needs to be able to see the satellite as well. So that's another. So you can't put it inside the trees. You need to have a clear sight to the satellite. So there'll be things to design and think about. One of the things thinking of things like HS2, or other new bits of track, but actually building natural bits of reflectivity into the track or into bridges. We know we can look at the bridges in London, and some of them are incredible radar reflectors, and some of them are almost invisible, which is why there are some artificial reflectors on Waterloo Bridge, because it's a very smooth bridge. The radar just bounces off it and doesn't go back to the satellite. So thinking about that when you're designing structures, so it's almost sort of like the reverse of stealth fighter bombers, right? So you want you don't want them stealth. You want really bright radar infrastructure, and then you don't need to put new reflectors in. You just build it in from the beginning. But I think a lot of the things retaining walls and the kind of Gabion things, all those, that kind of technology will all be quite bright to the radar. It's just dense vegetation, and so things will get better. And if I give this talk again in 5 years' time, I can show you results from InSAR with a longer wavelength, and I think we'll get much improved coverage with that as well. Yeah. Are there any online as well? I don't know whether.
Yeah, it should.
I've not spotted any coming in online. If people can hear me online, they want to submit any questions, then please do so through the chat function, and we'll repeat them.
Tim, I was just wondering, if we do more electrification, is there an opportunity of just attaching some reflectors to the top of the mast, for example, so you have a regular bright spot and you could detect movements of embankments? And
actually the overhead gantries are pretty reflective anyway. Right. So when we've looked at HS1, for example, that's you have really nice signals, I think, coming largely from a lot from the gantry. So I think I think that will probably work without much. I think without much thought needed. Metal things tend to be quite good reflectors in general. Yeah, we'll see in a field, in an otherwise bare field, the electricity pylons will kind of be a row of good points across a field, for example. So yeah.
Right, we've had an online question from Tony Wilcock, who says, as part of R&D at Network Rail, are we looking at scaling up to use at network level? So I don't know if Tony's in contact with the people that do this at Network Rail, but I guess you are, Tim. So
yeah, I think the focus at the moment is kind of demonstrating on obviously we're doing it in the Kent region on the South East Trains network, and we would like, I think part of that R&D at the moment is demonstrating it works for a region, and I think once we've done that, the next stage is obviously to think about how to apply it and scale it up, assuming Simon Abbott and others like what they see from the results. As I say, we don't want to oversell the technology, and part of what's happened in the past is that people have come in and tried to oversell InSAR as a solution for everything. And I hope I didn't do that and try to get you excited about the technology, but also show that it doesn't always work. And so trying to be a bit more pragmatic about, okay, it works here, it doesn't work here, but let's at least use it where it works. That's kind of, I think, that's where I'd like the answer to go, and we'll have to see, I guess, whether the geotechnical team at Network Rail think the same, and partly dependent on the results. I think the results so far are very encouraging, but we're about 2/3 of the way through that project. So the next big thing is the corner reflector installation, which is coming next.
Right, and also we've got something from Michael Furness. I don't know who Michael works for, but he says presumably the rails themselves are good reflectors. Is that the case?
Yeah, and I think that's partly why we get, when you look at a railway through a rural area, you get more reflectors along the railway. It's not, so the radar wavelength is about 6 centimeters, and so they're relatively small, and also, of course, it depends slightly on orientation. So it might be part of the reason we were getting better results in east-west oriented rails rather than, so I was expecting north-south ones to do better because for reflections off the rail, but perhaps it's things coming off the sleepers. I don't know. I'm not sure whether they would give enough of a reflector, but this is speculation. But I think the rails would have to be exactly aligned, because if you think about it, there's almost like a mirror. So if you have the mirror not pointing straight back at the satellite, then we might not get a bright signal back from the rail itself. But the ballast around it should be quite good. But the problem is the ballast gets reset, and so you're not necessarily looking at the same scatterers through time.
The rail fastenings, for example, might be.
Yeah, they might be good. Yeah.
Yeah, Tony Wilcott got back and said thanks for your answer, and he appreciates your objective approach.
Okay, good. I'm not sure the SatSense CEO appreciates it.
Who owns the satellites and be turned off or our price is high?
So Sentinel I owned and operated by the European Commission. So it's a part of a program called Copernicus, which is a massive investment that was made by, partly driven by the UK when we were still members, to kind of join forces on Earth observation satellites. So it's the biggest Earth observation program in the world, and the only threat to it, I think, is so the UK is still said it is going to buy back into it, and the same as the Horizon 2020 science program, but we haven't signed on the dotted line yet. The UK pays about, I think we're about 13% of the budget for Copernicus, and so obviously that's a big chunk if you lose that. But the satellites that exist will carry on, I think, and they have the European Commission set a very clear free and open data policy. So even if we're not paying for it, so people, the Americans can get the data, anyone anywhere in the world can get this data for free. There's no commercial restrictions on it for that side of things. So I think, I don't think there's a risk in that regard. I think it will be the opposite in many ways. We'll get more satellites like that. The other interesting space then, interesting area, is the kind of new space technology companies. So I mentioned ISAI, which is launching these very small radar satellites and launching tens of them. So you could actually then have them in a big kind of train and get daily images, for example. Those are obviously much more uncertain and unpredictable how that will go. They are always going to be commercial and activities, I think. And so, but in the end, if we're talking already in the 24 years I've been using this technology, it's come on incredibly, from looking at a single pair of images and doing years of work on that to actually looking at thousands of images automatically, and and I think the data is going to get better and better. So I don't think there's a risk of this technology going away. It might be we switch from one preferred satellite to another, but I think the technology is here to stay, I think, and it will get better. Yeah.
Okay, any more from in the room? No, okay. Last call for the questions online.
No, online questions have ceased.
Okay, in that case, I'll hand over to Andy for the vote of thanks.
Yeah, okay. Well, Tim, thanks for a very fascinating talk. I mean, we live in interesting times. There's so much technological advance going on at the moment, so many new technologies coming on, which might have applications in all sorts of areas, all sorts of industry sectors, and this clearly is one of them. And many times I've heard people say, oh, you know, we don't want a solution that's looking for a problem, but I tend to take a slightly different view to that, because I sort of think, well, if there's people with problems, they ought to be out there seeking what the solutions are, and people ought to be just saying what these technologies are in an objective way and what their limitations, etc., are, and then a match can be found, and hey presto, you have got a solution to a real problem. So yeah, I wish you and SatSense all the very best with this. I also hope that it goes really well with the work that you're doing with Network Rail. That's turns out to be an excellent collaboration. It would be nice, again, if this could be added in with some of the other technologies there to come up with a really finely honed optimal solution. So the track recording vehicle information would perhaps be an example of that. Thanks also for coming down here all the way to Derby from Leeds. We've been sort of pioneering today, trying to get back into the room after COVID, and you know, we have had some people in the room. We've not had the numbers that we may have seen before, but it's been nice for everybody to be here, and it's been great that we've been also able to have people online. This is the first time we've ever done a hybrid meeting. I think it's been a success. I'd like to thank Mark from DRES for sort of pioneering the technology that's put that together. I'm sure we can all learn something from that. But I'll stop banging on now and just say thank you very much, Tim. That was an excellent talk. And if people could give thanks in the normal way, that would be appreciated. Thank you.
Thank you. Thanks very much. So it's a pleasure to have a real audience. So that's the first first talk for a long time in front of a real audience. So it makes it so much better than staring into the void and speaking. So I appreciate I'm speaking to the void as well from to those there, and it's great actually that people. I saw that some of our colleagues from Network Rail who we're working with were online as well, so they were able to check I was saying. I'll see whether I get told off for saying the wrong thing. Hopefully I did run the slides by them beforehand. But so if people want to, I can kind of do